Welcome to this explainer. If you've ever stared at a pros and cons list and thought, man, this just isn't cutting it for such a massive decision, well, you're in the exact right place. Today, we're going to unpack how to navigate incredibly complex choices by shifting our thinking from rigid, old-school models to highly dynamic networks.
So here's a question to kick things off. How do you make a fair decision when your criteria are secretly working together? See, we usually assume our decision-making criteria operate completely independently of one another. But, think about buying a car. If you're judging based on speed and engine power, those aren't truly separate things, are they? So what actually happens to our choices when these factors are secretly influencing each other? All right, here's our roadmap for today. We'll quickly cover the flaw in simple decisions, the shift from hierarchies to networks, interdependencies, outer dependencies, and finally, we'll peek inside the black box to see how the Analytic Network Process, or ANP, actually calculates all this complexity.
Section 1, the flaw in simple decisions. Let's dive right into how we usually tackle decision analysis and the fatal flaw that's actually hiding in standard practices. For years, the analytic hierarchy process, known as AHP, was basically the gold standard for breaking down complex decisions. You'd list your goal, your criteria, and your options. Simple, right? But AHP operated on this really rigid illusion of independence. It just blindly assumed criteria never interact. The newer analytic network process, or ANP, absolutely shatters that illusion. It assumes a network model where criteria are dependent and correlated, which, let's be honest, brings our math much closer to actual reality.
Moving on to Section 2, from hierarchies to networks. To really grasp this conceptual shift, we need to think about the physical geometry of how we map out our choices.
Picture the old, linear AHP hierarchy like a strict one-way street. Decisions flow top-down in rigid levels. You start at the top with the goal, like, say, locating a sports shop. Then you move down to the criteria, visibility, competition, rental cost, and finally you step down to the alternatives, industrial area, shopping center, city center. There is absolutely no room for elements to loop back, interact, or influence each other sideways. It's a completely linear flow.
But ANP? It fundamentally changes the game by dismantling that linear hierarchy. Instead of strict levels, we now have clusters. Complex feedbacks and dependencies are suddenly allowed to flow in literally any direction. Criteria can influence criteria, alternatives can influence criteria, and elements can even influence themselves. It becomes a true dynamic feedback network.
Section 3, interdependencies explained. Okay, let's look at exactly what happens when elements within the exact same group are secretly correlated.
This brings us to a vital concept called an interdependency. By definition, this is a correlation of nodes or elements that are located within the exact same cluster. Failing to account for this can wildly skew your final evaluations, mostly because you end up unintentionally double-counting connected factors. Let me show you exactly what I mean here. Imagine a school rewarding the best student based on 3 criteria: language, mathematics, and physics. We're evaluating Shakespeare, who excels in language, versus Newton, who obviously excels in science. Well, the old AHP method unfairly crowns Newton the definitive winner. Why? Because math and physics are testing a very similar scientific skill set. Newton is basically double-dipping his advantage. But the ANP framework spots this interdependency bias, adjusts the weights, and perfectly levels the playing field. Suddenly, it reveals Shakespeare and Newton as much closer rivals.
But wait, what if the choices themselves are correlated? Like what happens when 2 options you are considering are practically identical? Welcome to the evening dress dilemma.
Picture this. A woman is choosing an evening dress for a big gala. Her initial choices are dress A, which is highly elegant, and dress B, which is a bit less elegant. Naturally, she strongly prefers dress A. But then, a third option, dress C, is introduced. And dress C is almost exactly the same style as dress A. Suddenly, the woman worries about someone else wearing the same style to the event. Because A and C are so similar, they have an interdependency. They literally cannibalize each other's appeal. Nobody wants to wear the exact same outfit as someone else to a fancy party. The ANP model captures this negative correlation mathematically, which makes the unique dress B the surprise, definitive winner.
Section 4, outer dependencies and feedback. Now things get even wilder when these dependencies cross over into entirely different clusters of your decision.
So an outer dependency happens when there's a correlation or a feedback loop between two separate, distinct clusters. For instance, when the importance of your actual criteria shifts dynamically based on the specific alternatives that are presented to you in the real world. Let's actually stick with that dress example. Suppose your initial criteria dictate that elegance far outweighs price. You're presented with option A, which is gorgeous but shockingly expensive. Option B is much cheaper but definitely less elegant. In a simple linear model, you'd buy option A because elegance was your top priority, right? But in reality, the staggering price of option A causes some serious sticker shock, and that feeds back into your criteria cluster. The alternatives are actively changing your priorities. This outer feedback causes you to suddenly prioritize price over elegance, and you end up buying the cheaper option B. ANP is specifically designed to formally map this exact type of criteria-shifting feedback. Section 5. Inside the black box. Okay, so how does the NMP framework actually calculate this incredibly complex, intertwined web of choices without just breaking down?
Well, it relies on something called a Markov chain. A Markov chain mathematically models random transitions from one state to another without any memory of the past. It's exactly like mapping the probability of 4 kids, let's call them Tom, Sam, Liz, and Franz, passing a ball to one another. Tom has a 50% chance of passing to Liz, a 30% chance of passing to Franz, and so on. AMP uses this exact same logic, but instead of children passing a ball, it maps the probability of influence passing from one decision factor to another. All of these dizzying transition probabilities get gathered into a massive partitioned framework called a supermatrix. Think of it like a giant spreadsheet of influence. It painstakingly records the direct influence of every single node across all the clusters. Goals, alternatives, and criteria are all plotted against each other. If there's an interdependency, it gets logged. Outer dependency, logged. It creates a complete numerical map of every single relationship in your decision network.
Then, to find the true mathematically sound winner, the AMP software runs a 3-step dance. First, it normalizes the columns into what math folks call a stochastic matrix, which is really just a fancy way of saying everything adds up to 1. Second, it repeatedly raises this massive matrix to sequential powers. And why does it do that? Because squaring and cubing the matrix traces the echo of indirect, cascading influence of every factor as it bounces through the network over and over again. Finally, this whole process settles into a stable state called a limit supermatrix. Those final, unmoving numbers reveal your mathematically verified global priorities.
So, we've seen how ignoring inner and outer dependencies can completely skew a result, and how ANP actually maps the reality of our messy, interconnected choices. Knowing that absolutely nothing exists in a vacuum and our choices are intricately connected, it leaves us with this final thought. If every choice we make operates in a network of hidden dependencies, how confident are you in your last big decision? Thank you so much for joining me for this explainer, and I'll catch you next time.